All right, so let's begin. While we're waiting for everyone else to join, I think right now we only have 10 students in here, so there's still about like 18, 19 of you to join. I want to talk about a little bit of the feedback I got from everyone here. And first of all, thank you so much for letting me know about the general feedback because that's something I really need for this semester, especially so that I can figure out what's the best thing going forward to do to actually make sure you can get the most of this class. So first of all, I think for the assignments, I think this is roughly what I'm aiming for, about 12 hours or 15 hours per week. Uh, for a new, like basically for first assignment. The second assignment, I think as of now, it seems like you spend a little bit less time a week, which is that's a perfect amount of time. If it is getting too much, we should talk through. Right now, I'm gonna have the virtual office hour in Discord. We have a channel for this class, and I'm gonna talk about that a little bit. So right now, the consensus midterm is way too long. As I said earlier, I would grade it as based on your code, even though it might not perfectly run, right? So I would go through your code, grade that in detail, and then I'll curve that. So once I finish all the grading, I'll show everyone here the breakdown. I would anonymize like the grades. You would know where you are relative to your friends in the class. I will tell you how the breakdown is, and then I would also tell everyone, okay, this is the curve, and then at the end of the day, as I said, I'll always curve up, right? I'm not gonna curve down. I'm aware that this is apparently way too long, so I would figure out what is the best way to address it for the final. But keep in mind, the final will have a little bit more of the written exam rather than the coding ones, just because of the material. The material in the final, some of it would be the background that you need to know for the OS class and any system class going forward. That would be generally useful. So some of those would be a written exam. There might be some open-end questions similar to the first question from the midterm, and I'll make sure that is within the scope. Uh, the actual coding practice for the final, you'll get in assignment 4. So there'll be some part of the assignments that would cover things like caching and virtual memory. The final would be more or less written. Uh, One more thing is this is a great feedback. Everyone, I think a lot of people here leave the feedback that there should be a live coding because there's a big discrepancy between after this class because I talk about the theory of like how C should be done, how to declare things like a pointer and etc. etc. But there's no such thing as an example coding. So going forward from this class onward, I'll try to use the collab edit, which is the same editor, online editor that we used from last Friday. Right now, my plan is to break you into groups of right now 5 to 6 people per group. Each one of you would pick one of the link that I'm going to show at the end of the in-class exercise slides. You pick one of those links, you'll be assigned to one of the team, and everyone in that team together would basically write the code for that in-class exercise. I will actually switch between all those 5 links so that I know how each team progress for the coding part. And then I'll manually tell, okay, team A, this part is right, this part is something, this is what you might want to do to edit so that it's correct or this is how you write it. And then I'll modify the code from here. So I think hopefully that gives everyone a good way to provide like, hey, this is an example of the real program, and then everyone can kind of like copy the code, compile it locally on their machine and run it. And then when these are not running, right? You can then come back, give me the comment in the chat or in Discord saying, hey, I tried, it doesn't run. This is the error that I got. So that I can say, okay, this is what you can do. Office hours guarantee 4 to 5 after this class. So on Monday and Wednesday, I'll be online in Discord, and I'll try my best to kind of like go through the questions. So hopefully this gives us like a much more interactive channel compared to email. The Discord for this class is now set up. You can go to system skill, both voice and the text part. I'll try to monitor those as much as I can. And feel free to take advantage of it when you have a question. I've been seeing actually students from the previous semester come in and answer the question that you guys have as well. So I think this is a good way to go forward for based on your feedback. And I'm like I would like to say thank you again for these suggestions. And now that we have everything set up, let's actually use it. And I hope it's going to be more effective going forward. I would try to provide more example programs and example codes. These are also great suggestions that would address one of the problems that we have, which is, okay, I throw you the assignments and then there's no sample. Might be a little bit too late for assignment 2, but for assignment 3 and 4, I would try to see what are the examples that I can combine with things like in-class exercise and things like our actual assignments and Discord to see what's the best way to proceed. Feel free to contact me if you need extra help. Actually, some of you email me saying, hey, I got sick. I would like to catch up. I'm going to watch the video. Actually, I don't mind if you need extra meeting hours saying, oh, okay, these are my questions. Can you help me going through all of that? My only requirement is sometimes, depending on my schedule, I might need to do it either during the weekend or like after 5 p.m. Right? So these are case by case things that I don't mind spending my time to make sure you can understand the concept as well as understand some of the possible I guess compilation errors or bugs that you see from C that these bugs are new, right? So I totally understand your frustration regarding the new language. And I would like to see how can I help. What else? Oh, okay. So there's one comment that I also appreciate a lot, which is I tend to get sidetracked. I tend to get excited easily when it comes to like computer systems, right? So if I do get sidetracked and somehow I forgot to answer the question or forgot to address the question, please let me know through the chat because I read the chat, but sometimes this thing get pretty quiet, right? So if I get overly excited and go sidetrack and then I forgot, please do remind me of that. I don't mind at all. Like I really want to make sure you catch up to not just the topic that might be useful in the future, but an actual topic that we're supposed to cover, right? So these things are things that I would like everyone here to help me a little bit too, because sometimes when I get sidetracked, it happens, and sometimes I forgot to come back. One last thing, if you send me email, because actually some of you said, hey, I'm not totally satisfied with the rate at which I reply to email. So I might have missed your email. That is possible. One thing that can definitely help is on the subject line, can you add that bracket that say MUIC-SysQ? This allows me to search in case I miss anything. Right? So these are the things that I would like you to be aware that, hey, I'm trying to see how can I improve the class, the format, and your learning experience. If there are any more suggestions, I'm welcome to that. And I'll try to address it as soon as I can. Sometimes things are not addressed as fast as I would like it to, but I'll also try. All right. Any questions based on all this midterm feedback and everything? Because we have actually quite a bit of material to cover today. All right, so no one say anything so far. I assume there's no. Okay, sincere request to extend deadline assignment 2, if possible. Oh, okay, because basically assignment 2 is on the same week as many midterms. Is that correct? All right, so more than one of you say yes. I would assume that's a yes. How about this? I would do the same thing as assignment 1. If you can submit it on time, you get 10% extra credit. Otherwise, oh, okay. So uh, otherwise you will get some extension for assignment 2. And then I'll post assignment 3 by the original deadline of assignment 2, so you can see the next assignment. How about that? Basically, for those of you who somehow managed to finish assignment 2 by the deadline, you will then get rewarded with extra points. For those of you who need more time, you get time. I'm not sure how much, how many days yet, but there would be extension. When can you? So let me decide that a little bit, because right now I want to check back at your midterm schedule a little bit and see how much I can, how much I would like to. So another question is like, okay, let's say you get full credit for the assignments. How does the extra credit work? You actually get the 10%, but I'll add it to some other categories that you missed. For example, you did not do well on your midterm, the extra credit would go there into that category. Right? This way, I hope I do reward people who start things on time and who would like to finish everything on time. And I'm not going to penalize people who suffer from multiple midterms. But I have not decided on when would be the good day to set the deadline for assignment 2. Anyone who thinks that's not a fair thing, let me know right now. If you think that's fair, you can say stay silent. If you think that's not fair, maybe I finished like 2 weeks ago. Then voice your opinion. Because as I said, I think the only thing the most important thing that I care about right now is the learning part, right? Because if the deadline comes way too early for everyone here to learn, that's not a great way to have the assignment. So uh, I would rather okay, so let's have a vote because that was being suggested. All right, so there you go, the vote. Let's see what everyone thinks. There are two options for a yes, and it seems everyone want more days for now. So what is your opinion? All right, for the three of you who have not started, and the one of you who are still deciding, I'll give you maybe 30 more seconds for that. But it seems like we would extend it by 5 days, because it's pretty overwhelmingly toward that, for now, unless everyone, okay, yeah, even more people saying, hey, let's do 5 days. All right, so let's we close the poll. We will extend it by 5 days. I would release assignment 3 early, and be aware that if you keep delaying your assignments, at some point you have fewer and fewer days on the last assignment. So if you are still on track, uh, you will then have more time on assignment 4. Okay, so I think, sorry, I think it was too loud. I think we have the decision here. I hope everything in this bullet point address most of the concern, including the detailed comments that you have. And again, I appreciate all this feedback. If there are anything that I missed, feel free to let me know one way or another. I don't mind. Just want to make sure everyone learns. All right. For now, let's come back to our material. What is it? Okay. Can you rephrase the question? So the summary of assignment 2, basically, if you submit on time, you get potentially 10% on top of your grades. If that go over 100%, that goes into basically any other categories. The extra credit can spill over into any categories based on the percentage. Uh, for uh, for people who still need time because say you have 4 midterms on this week or last week, then you can extend the deadline by 5 more days, 5 days. So you have 5 more days on that, but then I'm not going to make assignment 3 due earlier. Oh, I mean, I'm not going to delay assignment 3 due date. So if you use 5 days, please be aware that you're going to have 5 less days, like 5 fewer days on assignment 3. You pick how you want to manage your time. Personally, my recommendation is like if you miss the dead, like the original extra credit deadline, try to finish it as fast as possible so you have time for assignment 3. Or at least look at assignment 3. Because one of the things that I realized is for people who ask me questions about assignment 2, especially once they got to the point of, okay, this is how I implement linked list. This is how I implement the queue. They would do well on a midterm because that is the step up. And I do understand that it is like only 10 something days before the midterm. Uh, the trimester schedule make everything pretty tight. That's why I release assignment 2, and that's why I delay the midterm. That's why you can actually look at assignment 2, think about it, and try to implement it. I would encourage everyone to do the same for assignment 3, because assignment 3 is actually a lot more thinking and a lot quite a less coding than how it should be. You would deal with a lot of logical operations, and you think about how you would do it as cheap as possible. So it requires a lot more thinking, to be honest. So take a look at assignment 3 when they are released. That would help how long it takes to finish assignment 3. All right, so let's come back to the class material. We left off around the part where, okay, when you have the C language or Java or Python, the compiler is responsible for converting that to something the computer knows, which is the assembly code, right? In fact, it's not even assembly, but it's a binary. In assignment 3, we'll ask you to actually do this conversion from assembly code to binary. It will be a simpler version of the the assembly so that you don't have to do the full-blown x86 conversion. Otherwise, that would take too much time. Basically, once you run GCC, the compiler would convert that into ones and zeros. The ones and zero where the computer knows what is happening. So let's take a look at the assembly code by going through example. So let's say you have this really simple piece of code. I initialize A to 0, I initialize B to 5, return A plus B. Right? This is really simple. In C code, in Java, in Python, no more than 3 lines. If you want to see what is the assembly code responsible for these function in main, right? You can run obj dump -s followed by the file name. So let's say you compile it and this name is say a.out or your name dot something. You can say obj dump -s with that file name, and you will get what you get is a code that looks like this. Notice how the function name remains here, right? You see the function name, and then you see tons of things here that represent just numbers. The numbers here actually is we'll keep explaining this, but the way you look at it is these numbers here represent each of these instructions. So 55, this number 55 here means that from the computer point of view, it knows that, okay, this is the command it has to do, push RBP. We'll talk about what this means in a bit, but basically you can see that when you do obj dump or object dump, right, you get both the binary on the left side, so these are binary. These are the assembly. You get both of them. So let's go through what are these cryptic things. As I said, you have the function names right over here. This is where the function begins. This is the address of your code where they are in DRAM. As I said earlier, every single program is also a part, like it is a data. It's the data that is in your main memory, in your DRAM. So these numbers to the left that I highlight here are the address. Where is this thing in DRAM that I can run the program, that I can access the program? Any questions so far? So basically the number to the left represents the address of where my program is. Basically, my main function starts at RFA inside my DRAM. Note that it's a virtual address. We'll talk about that toward the end of this class. Just for now, just make sure that, hey, this is the program. This is the address of my program. These numbers are hexadecimal numbers. So these are hex numbers. These are actually instructions. It represents the actual instructions that the computer know exactly what they are doing. Inside the CPU, when you zoom it in, every time you execute those instructions, you will literally, if you somehow have a microscope that can see electrons, you actually see electrons going in that represent that exact number in binary in the CPU. It will say, okay, do this instruction, followed by this instruction, followed by this instruction, followed by this instruction. And then the CPU will have a circuit that break this binary number down into like, okay, if I need to do this add, for example, this add instruction, I want to do an add, This is what I need to do in the circuit to make sure I do this particular add instruction. This part, right? The one to the right, as I said, is the assembly code. It's what does this bits 0, 1, D0 here means in terms of assembly. What is 0, 1? 0, 1 is, so if you look at this, 0, 1 is basically 0, 0, 0, 0, 0, 0, 0, 1. What is D? EF, so that's 1, 1, 0, 1, and then 0, 0, 0, 0. It's a 2-byte instruction. This bit pattern means that I'm doing an add by adding these two values together and then put the result back into the first operands. We will talk about how add works in a little bit, right? So just right now, understand that to the right, you have the assembly code. To the left, you have the binary or hexadecimal number that represent that exact assembly code. You can see that sometimes these code has a similar thing because these are actually flat like number. You can actually embed number into your instructions. It would do certain things. As I said, these are the actual bits that represent this add. And there are, in general, if you want to build a computer, right now, you need to be able to support 3 types of instructions. The first one, obviously, you need to be able to do computation, add, subtract, multiply. Any question about the compute instruction and what they are? Hopefully, well, if you have still have any question about what does compute instruction means, you can ask me afterward during office hour. The second type is memory instruction. These are instructions that move the data from DRAM into the CPU or move the data from the CPU back into DRAM. Think of this as your computer scratch pad when you need to put in some intermediate data, right? You have to put data in and out between the CPU and DRAM. The last type is we call this control instruction. It determines what is the next instruction that I need to do. In most cases, the next line, right? What would be the exception of this? Why would I not running the next line of code? Can someone give me some example? Break is one of them. That's a great example. You can return. That's another great example. You would then run another totally different instruction, right? Because it's a different function calls. Another example is if else, right? If this is true, you run the next line. Else, you jump from this block of code to the next block of code, right? So you don't go to the next instruction, you jump somewhere else. For loop, for example, instead of the next instruction, which means you exit the loop, you need to go back to the beginning of the loop. So you jump back. Right? So these are what the control instruction is for. It basically tells you how you would proceed based on the program, based on how you write the program. Here is what I mean by opcode, right? So I talk about both opcode and operands in the earlier slide. What is opcode? Opcode is basically what am I supposed to do with the instruction? It tells I need to move data around, move, M-O-V. I need to add something. I need to push something to the stack. I need to pop something to the stack. So we talk about the stack pointer in a bit. Right now, just think of it as that is a stack in computer system that is handling something. And you can do a push and you can pop. Return means that I'm going to return from this function calls. What would happen if I return from the main function? Exactly. The program ends. Does it mean the computer ends? Nope. Yeah, that's a great. Yeah. So basically, think about it, right? When you run a program, you run it under another program. Why? You boot up Linux, you boot up Windows, right? Windows and Linux are also programs. The program calls another program. So when one program ends, it's like when you play games and you exit, right? You come back to Windows. The computer doesn't get shut down until you literally hit the shutdown button. And in the OS, you then learn that when you hit that shutdown button, there are actually multiple programs that would get called to handle, hey, let's save all the data, let's save everything, making sure the next time the computer is powered on, everything runs smoothly. Right? This is this is actually called SIGKILL. So whenever you hit something on the computer, it actually sends signals to the OS saying, hey, do this, do that. Reboot the computer, restart the computer, shut down the computer, then interrupt. I'm typing something, draw this on a monitor. So basically, when you have this return function, basically it returns to the whatever caused this before. In this case, it's the main function. So when you finish the main function, the program ends. The program that called this program will resume the execution. Windows would come back and do whatever it has to do. What is the operand? The operands is here on the right side. Basically, these are the object of my instruction. What do I do? Right? Where is the data that I'm gonna add it with? Where is the target that I'm gonna write the result into? Right? And the operands also sometimes can be address, right? Something like this, where it's just a flat number. It's an address inside your main memory. It can be relative. It can be like a basically a number without any relative. Like in this case, 0.0 means that I'm referring to this location of my address, and I don't move around. It's that exact match. 0x5 followed by negative 0x4. It means that I'm gonna start from RBP as my initial address, and I'll go 5 steps from there. 5 steps, right? It's kind of like when you refer to A0 and A5, something along that line. So everything, it can be relative to some certain value. So this is the operands in the format of register, and we talk about register and what they are. In the next slides, basically RBP is a register. So okay, that's a great question. So there's one question on these binary on the left and the instruction on the right. Are they the same thing? Okay, so let me handle the first question. Are they the same thing? Yes. The left side is what the computer see as a bunch of ones and zeros. The right side means that these one and zeros means this instruction. The second question, what is negative 0x8? That's negative 8 in hexadecimal. 0x means that this number is hexadecimal. 8 is literally number 8. Negative is negative value. So you can represent both positive number and negative number. All right, so hopefully that clears up the two questions. Basically, the binary on the left side, the number on the left side, correspond to the instruction on the right side. Okay, that's another great question. So the question is this push? Actually, that's not push. This is push. 55 is push RBP. This is the address of where the number 55, which is this instruction here, is located in DRAM. Because if you think about it, right, your program, this is DRAM. Your program is somewhere in DRAM, and you need to be able to tell you, okay, that's the line I'm running right now. See, 5FA, this thing 5FA correspond to this location. So this is 5FA. Inside this line, inside this exact line, it will be 55. Think of it as 5FA is a pointer, and my data is 55. That data represents push RBP. The pointer points to that instruction. The pointer is just an address. All right, so let's talk about register. I'm gonna have another figure that tells you what is the register, but right now let's define it in theory. So basically, what is register? Register is really fast, but temporarily storage inside the CPU, right? Because right now, the way we understand it, everything that relates to the data are in the main memory. But your computational unit, the ALU or the CPU, is on the CPU, on that processor, right? How many of you have seen a main board before, a motherboard, where you have the CPU and you have another slot that you can plug in DRAM? Let me see if I can get a sample of that. It's not good sample from Google. I don't know why. Okay, I think this might be good here. When you see the motherboard, right? When you buy a computer, this would be one of the main part in your computer. This thing is where you put in the CPU, the processor, those Intel and AMD processor. This one is specifically for the Intel processor. You put it in here, right? Then this is where you put in DRAM, right? So what happened is when you need to access anything in DRAM, when you need to access anything in here from the processor from here, you actually need to make sure the electrons move from DRAM all the way to the processor, which it takes time, right? It takes time to move from here to here to here. It has certain distance, which means that accessing these data can be slow. So the key here is accessing these data is slow. You don't want to move to DRAM every single time you need to do an add. The idea of register is, okay, instead of storing everything in DRAM, what if I have a small set of variables that I can store temporary data inside the CPU? Can someone think of the benefit of having this little amount of storage inside the CPU? So essentially, to get to that data, now it's on the CPU, so it's going to take a lot less time. There are actually multiple benefits. The main benefit is it takes a lot less time to reach that data, right? Another benefit is these registers are also visible to programmers, so you can actually manipulate it. I know that I have the 16 temporary variables that is going to be really fast. So I know exactly how I would write my program to make use of those variables, such that I rarely have to go to the main memory to get my data. Right? Every single compute instructions, things like add, subtract, multiply, that happen on the processor, it has to be done through this register. You can't directly access the main memory. Technically, you can with the current technology. We call that processing in memory. Unless you're gonna write papers about it, which in that case, do let me know because I work on that direction. But any any compute instructions will be done on this register. And we call a group of register file. That's the name, just memorize it. Basically, register files means that it's a collection of registers that you have in the CPU. Different chip would have different number of register based on the ISA. The ISA defined how many register you have for that chip. And here are the difference between register and memory. As I said, this is extremely fast. So you might have heard about the clock cycle, right? The frequency of the processor. These days you look at 3.5 gigahertz or something along that line, right? So let's say I have a 3.4 to 3.5 gigahertz processor. How long is one cycle? So let's say that's my clock speed. So how long is one cycle? So okay, that's another good question. Register. So the question is register in the processor, and the processor is on the main board. So essentially, when you buy a processor, you get just the CPU, right? The CPU is useless unless you have everything else on the main board and DRAM and hard drive and everything that connects into a big computing system. So when you buy a CPU, what you get is the CPU itself, right? The compute unit. You get the register that is on the CPU by default. It's in there. You will get another it's another small memory. We call them cache. You learn about what is a cache and how does it work in a few more lectures actually. So those are all in the CPU. When you plug that to the main board connects the CPU with the rest of your computer. It connects your CPU to DRAM. You connect your CPU to the PCIe, which connects to the GPU, right? So you can run games. It connects the CPU through the SATA interface, SATA, right? To connect that to the hard drive. This allow you to be able to access the hard drive. It connects you to the GPU, which then connect to the video interface, which connect to your monitor. That allows the CPU to upload something to the GPU, which then produce something on your screen, right? So the main board job is to kind of like manage and connect everything and making sure everything runs properly. So come back to my question. If I have a 3.5 gigahertz processor, how long is one processing cycle? The answer is one over this. That's how long one cycle is. This is roughly 0.3 nanosecond. So right now, in one single cycle, which allows you to do add, allows you to move data from one register to another. This takes about 0.3 nanosecond. Is that fast? It's pretty fast, right? For the main memory inside your DRAM, this is how long it takes to just access one piece of data. How many times longer? So my question right now is, comparing to access a data in a register, how much longer if I need to access the data from my main memory? What is the number I have to divide? All right, someone wake up and do some math. How much longer? All right, what's my numerator and denominator in my equation? What do I divide it by? I know I have the number 12. I know I have the number 0.3. What do I do? Yeah, more than 36 times, yes. So basically, in the best case, you are looking at 12 over 0.3, right? This is around 40 times. This is the best case. It is not subtract, it's divide. Basically, 12 divided by 43 because I want to see the relative between the two numbers. But you're looking at 40 to 100 times longer. It takes so long to go to my DRAM to get my data, right? And what's more, every single CPU core, right? So when you say multi-core, when you buy a processor, it comes with multiple core. Each core has their own register. But if you want to go to DRAM, those are shared amongst every single core. It's like you go to 7-Eleven and you want to buy something, but then everyone in that village also share that one single 7-Eleven, right? So you have to queue up. It does take longer time. That's why you want to put data inside the register and minimize the number of access that you need to go from get the data from the main memory. So any questions about why register are important and why it should be there? All right, so let's talk about another special type of register because we talk about, hey, register is this temporarily variable that you can store data for computation, right? There's another special type of register called program counter. Basically, this program counter, it doesn't store data. It stores that pointer to your instruction. It tells, this is the instruction I'm running right now. It points to that instruction. And then when you move to the next instruction, the way you do that is you update this value by incrementing them to the next instruction. That's it. That's the point of the program counter. It basically corresponds to the assembly instruction that I'm running right now. Every single cycle, you will then update this program counter based on what is the instruction that I am going to execute next. Typically, this is not always true, but you can think of it this way. Typically, every single cycle, you would try to increment this program counter. Right? This allows your program to move on to the next instruction. There are certain things that can happen to make program counter stays the same instruction. For example, if you have to load the data, which take a long time, in that case, the program counter won't go to the next instruction to run the next instruction because you haven't finished the load. Another case where it doesn't go to the next line of assembly code is when you have code branch, right? When you have control instruction, which in this case can be return, for example, that you said earlier, return, break, if else, loop, right? These things would overwrite the program counter to wherever next instruction is. It doesn't have to be the next line. In the context of programming, sometimes people refer to this as instruction register. Why? It's a special register that store instruction rather than a data. That's it. It's the same. It has the same meaning. Program counter and instruction register. Two words, same meaning. And now let's kind of briefly talk about register versus memory versus I/O. I/O is when you have to say write something to the disk or show something on your monitor, right? This is DRAM. These can be monitor, like the red thing can be monitor, keyboard, SSD, hard drive, right? Same thing here. You can also output things to SSD hard drive. So the monitor should not be here. The monitor definitely will be the output. Right? This is mouse. The processing unit, everything in blue is inside your CPU. So you can draw this wall here. This wall means that this in the CPU. This is DRAM, so you can draw another wall here. Everything in blue is really fast. Everything in green is kind of fast. I mean, faster than the red thing. Anything in red here is really, really, really slow. How slow? CPU and DRAM talk in nanosecond scale. Drive, hard drive, solid SSD, solid state drive, they talk in microsecond scale. That's how much slower it is, right? So you can see that there are a lot of communication here. Oops, my bad. There are a lot of communication here. And you can see that you want to make sure your data is in here as much as possible because they are the fastest. Then, if you can't fit that in, you can put your data in here. Let's say this is location 1, location 2, and your solid state hard drive is location number 3. In terms of speed, 1 is a lot faster than 2, which is a lot faster than 3. When you write the program, you might want to be aware of that. I want to put more things onto my CPU as possible because they are fast. Otherwise, if I need to do a lot with my data, how would I maximize things that still remain on my CPU? And we talk about register. So in the Intel processor, we call this x86-64. Do you know what the 64 comes from? Have you heard of the 32 bits versus 64-bit processor? Okay, so back in the day, 32-bit processor means that address is 32 bits long. 64-bit processor means that address is 64 bits long. It actually means multiple things, but one of the key differences is 32 bits long address and 64 bits long address. If you think about it, if I have 32 bits machine, how big can my DRAM be? So what's 2 to the 32? what is 2 to the 32? What is 2 to the 30? I already gave you a trick. 2 to the 10 is 1000. So what if I multiply 1000 3 times? If I multiply 1000 3 times, I get 1 gigabyte, right? I get 1 gigabyte of data. Okay, so repeat the question. What is 2 to the 32? That's the question. Basically, that is correct. So the answer is about 4 gigabytes, right? 4 gigabytes. It means that my address has a range big enough to support 4 gigabyte DRAM. How many of your computer only have 4 gigabyte of VRAM? Anyone still have a computer that's less than 4 gigabytes? My bet is no, right? Why? Okay. Your PC at home, yes. Then it means that it can still might be supporting the 32-bit ISA, right? Basically, one of the main downside of 32-bit ISA is it can't support, it doesn't have enough bits to represent larger than 4 gigabytes of DRAM. And when you have that restriction, it can be hectic, right? Because now program in many cases want basically it wants gigabytes of memory. So Intel and AMD came up with 64-bit ISA. They are actually competing, and historical fact is the AMD wins this war. Actually, every single processor you have nowadays, a 64-bit, come from AMD. It's actually called AMD 64. It's exactly the version of x86 that supports 64 bits. In this ISA, you have in total 16, right? 16 different registers from here that you can use. There are 16 of them. In each of the 16 of these registers, you can use different name, right? Because each of these 16 registers, a data is also 64 bits. So in 64 bits, how many bytes do I get? What is 64 divided by 8? 64 divided by 8. It's 8, right? It means that these registers can store up to 8 bytes. Up to 8 bytes. But what if I have a character, I just want byte 0. If I just want byte 0, I can refer to byte 0 of RAX, like this particular register. I can just do %AL. So instead of getting the entire 8 bytes, I'll get the first byte, byte 0. If I have a short integer which only has 2 bytes, I can do %AX, right? This will give me 2 bytes. If I have an integer is 4 bytes, so I can just do %EAX. This EAX is one of the most common register inside the assembly code that you see when you compile. It would give you just byte 0 to 3 from your register files. Byte 0 to 3. And then you notice that the way it goes is you have the number, right? I mean the letters A, B, C, D, right? These have historical reason. That's why you don't name it 1, 2, 3, 4, 5. To be honest, from the hardware point of view, we would love to rename that way. But can someone imagine what can happen if you rename this register? So what if I have an assembly code that I compiled in 1980 that still use EBX. And somehow the new processor use R0, I mean R2, right? In that case, I need to go modify my program. So the AMD solution was, I would make this name the same. I would make this name the same so that if I have the old assembly code, they would still run on the AMD ISA. You can run all programs, it would run fine, it would somehow execute, and it would get correct results. Otherwise, you need to update your program, essentially. The question is, are these the name of register? Yes, they are the name of register. So it has, as I said, 16 of them, right? The first 8 has special name, A, B, C, D, as I said. There's source and destination index, which has some historical reason, but it's another 2 register name. These are 2 special register that you don't really want to use. If you want to use more registers, just use 8, 9, 10, 11 to 15. So after register number 7, everything is just numbers 8, 9, 10, 11, 12, 13, 14, 15. The stack pointer and base pointer has something to do with function calls. So we're going to talk about it in the next lecture. And that's why you don't want to use it, because otherwise your function, when you return, it might be wrong. So just bear with it for now. When you have ESP and EBP, it deals with function calls. Right now, the next thing I want to tell you is how to move data from the main memory into the register, or move data from one register to another register. So you can use the MOV command here. Right? It's one of the assembly command that can be moved. You can use that to move data from register to another register. And here's the example. You can run move Q. Move Q can be changed to B, which stands for byte, word, or no suffix, which is just a typical move, which would then move the entire thing. The operands that go into the source and destination, they can have different types. You can have immediate. When I say immediate, it means like take that number of bits as number. For example, if I say MOV, move $10, these are constant data. These are also constant data. So what's the difference between $10 and $0x2a? $sign means number. $10 means literally number 10. This is a hexadecimal number that represents 2a. Right? You can also put in register. So if you're trying to figure out the example, I have that in the next slide, so you can wait. Right now, I can. What I want to say is things that can go into source and destination. You can have register name like EAX, RAX, EBX, R9. These can go into source or destination. You can have memory plus register. These has to do with addressing mode, but essentially, you want to move these number of bytes from DRAM into the register. So here is some example, right? If the source is immediate, something like this, what this does is basically I'm going to assign the value 4 into RAX. Okay. Here. So when you write your own assembly code for the first time, you can always come back at this example. This is, I think, the exhaustive example of what you can do with move. You can move a value into an address in DRAM by using this parenthesis. The parenthesis around register name, it means that treat that value as an address. Basically, it's a pointer. It's a pointer that represented by the value RAX. This is the same thing as this command in C. Star P equals -20. What does this do? It would look at where is this value in the DRAM. The value is represented by P, and you put in 20. You can do register to register. This is probably one of the most obvious ones, right? You assign the two number, R9 and R10, basically put the whatever value R9 is holding, copy that to R10. You can then put a destination in the address format, which then you just put parentheses around it. This is register to memory. Right? When you do this, it's essentially the same as star A equals B. You write the value B into pointer A. Pointer A comes from R10. B, the value comes from R9. You can then move something from, say, here, DRAM, right, into the register is on the CPU side, right? You can use move, put parentheses around the source. It means that whatever R9 is pointing, I want that data into R10. And this is the equivalent C code. So you can always come back to this example. I hope this is clear enough that, hey, you can put multiple things into source and destination. It depends on that. Whatever's in the source get moved to the destination. It can be address or it can be register. Why is M a capital? Typo. My bad. It should be lowercase. Thank you for spotting that. It should be move Q. So let's talk about addressing mode. Right? Basic addressing modes define how we obtain the operands. There are multiple types. You can have the absolute type. We'll talk about this in detail in the next slide with examples. Why is R10? Okay, that's another good spot. This is typo. You should be %R10. Thank you so much. Move Q lowercase, percent in front of register. Percent means that whatever comes next is a register name. So it should be %R10. Thank you so much. All right, so let's talk about addressing mode. Addressing mode means that I can refer to the address in DRAM with different methods, right? We've seen earlier, if I put parentheses around register, it means that the value of the register becomes my address. There are multiple other types. For example, you can do the absolute where the address is just this number. That's called the absolute addressing mode. You treat the number as an address. Register indirect, which is what we see earlier. If I put parentheses around register name, that means that the value I'm loading is coming from whatever address is represented by that register. You can then use a displacement base where you have an offset followed by R1. Basically, this is what it means. You start with whatever value R1 is holding, and you add additional offset. Offset is just a flat number next to it, right? Loaded into R0. And then each ISA would have the different definition of how this is done. And before we go through an example for x86, I I want to tell you why, right? This seems kind of complex. Why would you need that? So if I have a 64-bit machine, it means that my address is 64 bits long. So if I want to do a load, using always using the absolute number, it means that I would need at least 64 bits to represent the address I'm loading. That's long. Your program, the size of your program would go up and up and up because you need to specify always 64 bits. So instead of using all 64 bits, you can either use a register value. This actually allows much easier time for the programmer to hack assembly code. You can use another value for the offset. You can use another register as the base, or you can even add a scale. So instead of going by 1 byte, you can go by 4 bytes at a time, or 8 bytes at a time, or 128 bytes at a time. It allows you to move around in this address space quickly. So here are x86 addressing mode. This is the overview. This is what you can write in source or destination. It goes into this format. D in parentheses, 2 possible register followed by 1 number. The scale can go up to 8, 1, 2, 1, 2, 4, 8. The scales mean that how much I would want to jump. It's a jumping by 1 byte, 2 bytes, 4 bytes, or 8 bytes. D is the displacement, base, and index. And here is a formula. If you put in D in parentheses RB, RI, and S, this is what you get. Basically, you start with 3 components. You start with the base plus, right? Plus S multiplied by index, and then plus the displacement. Displacement, somehow we call this offset. Basically, that's my address. If there are 2 registers, you start with the first register as the base plus S multiplied by the second register plus S. So let me go through some example. What if I put in $10 percent EAX and EEX and 2. And in this case, let's say EAX is 0x1000 and EBX is 12. Like the actual value 12. What is my address here? So what is this part? What is my base? EAX, right? So you have, 0x1000 plus, what is S? S is probably the easiest from here. What is S? S is 2. S is 2 multiplied by, what is the index? Index is EBX, right? So what is EBX? It's 12. What is my displacement? Displacement is whatever is in front of this parenthesis, right? Which is 10. So these represent the address 0x1000 plus, what is 2 times 12 plus 10? 34, right? So how do I add a hexadecimal number with a decimal number? Can someone tell me what's the result of this? Okay, so the question is, I didn't understand where did 12 and 10 come from. 12, which is the index, right? These index come from Ri. Ri is the second argument in my parenthesis. What is the second argument of my parenthesis in this example? EBX, right? This one. This is my second argument. What is the value of EBX? Our assumption is EBX is 12. So you just put the number in. 10, what is 10? 10 is the displacement here, which comes from whatever number is in front of that parenthesis, right? Which means that I'm going to take this number, that's 10. So basically you have 2 multiplied by 12, right? 2 multiplied by 12 plus 10, which comes from here, which will give you 0x1012 in hexadecimal. Why? 34 is 32 plus 2. 32 is 0x10. 2 is 0x2. So you add the three numbers together, it's 0x1012. All right, any questions? And the summation come out of, yeah, so basically after you have this, you can convert it to decimal number as well, that's also fine. If you want a decimal number, just don't put 0x on in front of it. If you don't put 0x in front of it, people would think of that number as a decimal number. If you put 0x in front of it, it will be a hexadecimal number. That's a convention that everyone would understand, basically. So it can be a decimal number. It doesn't matter because at the end of the day, both numbers are the exact same value. All right. So any question about addressing mode before we move on? Why is it? Okay. Why is 0? Oops. Why is this turned into 0x1012? So this is basically 0x1000, right? Plus 32 plus 2, which is the same as 0x1000 plus 0x10, right? 32 is 0x10 plus 0x2. Basically, if you convert everything to hexadecimal number, it will just turn out to be 0x1012. Okay. So summation is just binary arithmetic. You have 0x1000, right, plus 34. 34 is 32 plus 2, right? So this basically means that I have 1000, right, plus 0x10 plus 0x2. This is 32. This is 2. And when you add the three numbers together, you get 10, 12. All right. So if you still have a question, get the coffee and yeah. So just get a coffee. I'm sure you get it. Basically, just add the three numbers together in the same base, hexadecimal base. Okay. So let's do a quick example of, hey, what if we want to write a swap function that this is the only thing you do. You take in two pointers and you swap the number, right? This is what you assume. So how would I write this using MUIC? Actually, let's do this. Let's try out the collab edit. and see if this works well. So give me 30 seconds because my internet is so bad to generate the blank file for you. Oh my God, so. Okay, so can you go to this link? collabedit.com slash pswfy pocket.com. So if you go there, this is what you see. Let me share the screen quickly. Here, you see this, right? So forget about this part. I'm gonna use the scratch pad down here. This is your code. In assembly. So let's assume that RGI is X, RSI is Y, and then RAX is temp1, and then REX is temp2. What would I do for the first instruction? My hint is you can do move Q. You can do for move Q to do this. What is the first move that I'm supposed to do? So what is temp1? What is temp1? Temp1 is RAX, right? So I can put RAX as my destination. What is my source? Source is X, right? But it's a pointer, so I want the address. So this is what I can put in. RQI, right? Because X is, oh, my bad. not RQI, RDI, hypo. Right, and someone put X here. So you have moving RDI, whatever address RDI is, right, which is X into RAX. Can someone fill in the next line? How do I assign temp2 equals star Y? This is the almost the same exact copy of the first line. Can someone type it in? I mean, you are many of you are in here. Type in something. All right, good starting point for sure. With the okay, I think it is getting chaotic, but interesting. Yep, direct the right direction for sure. And don't worry about multiple typing. I think as long as you get what you're doing, it's fine because I understand that many of you are typing right now, so there may be conflicts. So let me go fix the syntax a little bit here. All right, that's correct. Quick question: Is this is the source, right? So when I do star x equal temp2, temp2 is the source, right? And temp2 is data, so you actually don't need parentheses here. You don't need parentheses here because temp2 is dealing with the data. It's already stored the data. It's not a pointer. Then, yep, you got it almost. My bad. It's RBX. Okay, is this A or B? Can someone pick one? Is this A or B? All right, perfect. Yeah, so you guys got it. Right. You know what I mean, basically. Right now, it's just having multiple people editing the same file at the same time. So let me share my presentation again. Okay, so we're back, right, from the example that do swap. Hopefully you got an idea. Basically, you can go line by line and see, okay, is this an address or is this the data? And you put parentheses around the data and you don't put, I mean, you put parentheses around the address to make it behave like a pointer. And you don't put parentheses around the data because it's already storing the data. Here is the same example from earlier, but we already did it online. This is a little bit different from that example because our assumption is different. Now it's RBX, it's RGX instead of RBX. Let's go to the next instruction. So we have been using move earlier, right? So now the next instruction is another instruction that can use to compute the address. This is kind of like almost the addressing mode, but you can define an instruction for that. And here is some usage. You can quickly compute the address of this format, x plus k times y, using this particular instruction. Basically, it's an optimization that can make your program a little bit faster. And here's the example. Let's say I want to return x multiplied by 12. I want to return x multiplied by 12. I can use LEAQ to do x multiplied by 12y. This basically having temp equal to x plus 2 times x, right? This is the scale, the S. This is X, and this is also X. Notice that it's the same register. What you have here is X plus S times X, right? And S is 2, so this is X plus 2 times X. What is X plus 2 times X? Basically, that's 3X, right? This is 3X. X plus 2 times X, that's 3X. This is shift left, SALQ is shift left by 2. So what is 3X shift left by 2? Three x shift left by 2 means that I'm going to do 3x multiplied by 4, which is 12x, right? Shift left by 2, it means you multiply by 2 to the 2. 2 to the 2 is 4, so you get 12x. Why is this faster than x plus, why is this faster than if I want to do just multiply instruction? It's actually faster because multiply by 2 can be done by shifting. That take one cycle. Add take one cycle. So this whole thing takes 2 cycle. This whole thing takes 2 cycle, 2 CPU cycle. If you want to do multiply, that takes around 5 to 7 cycles. So that's why you can actually make program run faster. These particular optimizations. Sorry, my Apple Watch thing that I want to send some message. If you want to optimize the code like this right now, in modern day compiler, when you use GCC, forget about it. They'll do this for you. What this slide is for is just to let you know that, hey, there are many tricks you can do in assembly to make things faster. And these become relevant when you look at compiler. If you want to design your own compiler or you want to work at the compiler team in, say, Google or Facebook, they actually do have compiler team to optimize their code. These are things that you can do. Here are summary of common arithmetic operations. The name hopefully is representative of what they do. Add, subtract, multiply, shift left, shift right. This is logical shift right. XOR and or increment, which is plus plus, decrement minus minus, negate in the like put the negative sign into the destination. Not kill, which is put the negation. Oh, SAL shift arithmetic left. SAL is shift arithmetic left, so it's a arithmetic shift left. SAR is shift arithmetic right. SHR is logical shift to the right. You can look at different processor states, right? These are also visible to programmer. Things when we refer to processor state are essentially things that you can do in assembly, things that you can control. What are those? What are going into the register? The RSP, which we're not going to cover, we'll cover next week. But right now, just be aware that you can modify that. You can read and you can modify. Read and write, right? You can change the value of instruction pointer. Instruction pointer is PC, program counter, right? This is referred to as RIP. Not rest in peace, it's an instruction pointer. In x86, this basically tells me, it points to where my next instruction is. In some type of ISA, you can also check the status of recent instruction, right? It can be 0, for example, CF represents 0 flag. My previous instruction result in a 0. Let's say I do subtract 2 minus 2 equals 0, that flag would becomes 1. Overflow flag means that let's say I add 2 numbers and the 2 numbers just happen to go above 32 bits, right? Into the 33rd bits, you only have that many. Like, let's say you use 4 bytes, which means that this would overflow, so the flag would become 1. These flags have something to do with what we call condition code. The first condition code, which one thing that can happen is you have the carry flag, right? What is a carry? What is a carry when we add 2 numbers together? When does it have a carry? It's when you have 2 numbers like 5 plus 9, right? You get 4 with a carry of 1. 5 plus 9 is result in 4 with a carry of 1 to the next digit. In binary, that's the same thing. If you have a carry into the next digit, that is 1. 0 means that, yep, 1 plus 1 equals 0, right? But then you have to have the carry bit into the next binary. 0 flag is set to 1 when it results in the 0 value. This happens when you subtract, right? Or it can happen when you do this. 1, 1, 1, 1, 1, 1, 1 plus 1. This would set the carry bit. It would set the 0 bit. It would set the overflow bit, right? A sign flag is set, SF sign flag is set when the result of the previous instruction results in a negative value. Overflow flag is when the result of the previous instruction results in the overflow that 1 extra carry bit into the next bit that you don't have in store. And all this flags are set on every arithmetic instruction except for this. That instruction that used to calculate the address. Why is these useful? These flags can be used to compare, right? When you have if-else, the if-else statement allow you to compare the 2 numbers together. And this is typically set implicitly. When you run, say, CMPQ, compare source 1 and source 2, it basically do the subtract. You subtract source 1 and source 2. This carry flag is set if the most significant bit has a carry out. It carry the extra ones into the next number. 0 bit if the source 1 and source 2 is the same. Sign bit is if the left number is greater than the right number. If the left number, source 1, is less than the source 2. If source 1 is less than source 2, the sign bit is flipped. Why is that the case? Because what it does is it literally is doing source 1 minus source 2. And then the overflow bit is happen if the condition below fit, which is the 2 complement sign, the 2 complement format number is overflowing. This is the condition check of when this becomes true. Instead of compare, you can also, instead of implicitly set this flag, you can set it manually by using the command test, right? This command test source 2, source 1 would actually manually set the flag. This is the same as running source 1 and the logical and source 2 without writing any results. and then it would store the condition code in the another instruction called set instruction would store the condition code, right? This thing, the condition flag, into the register. It can be RAX, RBX, or R9, R10, based on whatever come up here. If you say set E, you just write the 0 flag into the register. Set NE not equal, so you write the negative of 0 flag. Set G, for example, would set greater, represent this sign bit XOR overflow bit, not of CF. You don't have to remember this. If you are curious about how set can be used, go back to this slide. I have already posted. You can refer to this again, as well as this will be posted on YouTube. You can use basically the set command to write the condition based on this table, this part of the table, right, into the register. Why can that be useful? Then you can use the register later. Sorry about animation, but the text supposed to come first, but basically only set the lowest byte of the register. Right? Register can have multiple bytes. This would set byte 0. And this should typically be paired with this particular move instruction to set the upper, like basically the upper 32 bits to 0. Otherwise, you're going to have jump data in your register because it's only set 1 byte. Here is an example. Let's say I have a function that just returns if x is greater than y. A function that just returns if x is greater than y. What I can do is first do the compare. Right? This is basically compare the two numbers. And this, what it does is it will properly set the flag in all those carry flag, 0 flag, SF, right? And then the overflow and sign, all the flags. Then you manually store the flag to AL, store AL, that register, right? Then you set all the remaining bytes to 0. The right side is the assumption. RSI and RDI are the input arguments. If you have any question about set, let's come back in Discord after this lecture during the office hour, or I'll basically, if it's after that, put in a question, I'll answer them. All right, because we don't have a lot of time left. We would definitely push the in-class exercise to next week because we run out of time. The next thing we want to talk about is the instruction pointer. This will point to the next instruction, I said it earlier, is a PC, and this is useful to implement if else. Right? And here is the jump instruction. The jump instruction basically modify instruction pointer, program counter, that special register to tell what is my next line of code. You put in the condition here based on the name. It can be JMP, jump, this is always true. Jump if equal, jump is not equal. Jump equal, jump not equal. Jump if the sign flag is true. Jump if the resulting earlier instruction is a negative number. Jump if the earlier instruction is not a negative number. Jump if the earlier instruction is greater than. Jump is greater than or equal to. Jump less than or equal to. Jump above and jump below. Jump above and below is just basically look at these two flags. Jump below is if source 1 and source 2 set the carry flag. Jump above is source 1 and source 2 result in no carry flag set, no zero flag set. And you can use this to basically implement if else and loop, right? If you have if else, the first thing you need to do is to compare the condition, whatever goes into the if bracket, right? And do the jump if the condition flag becomes true. Here's the overview of the jump instruction, right? This is, think of it as a go-to command in C. In C code, you can actually write in go-to and put in the line number. We don't teach you that because this is bad. Don't do it. Why is this bad? This can give you a lot of unexpected results. It can lead to more go-to. It can lead to totally unexpected line. That might not be a good idea to do that in C code, right? But in assembly with jump, because you know exactly what instruction is where, that's okay. The jump can be used to implement the loop. It can be used to implement if else. This basically allows you to have a functioning program. And you can do, okay, actually let's pause here because we are kind of out of time and there's only 2 or 3 more slides, but it's a little bit of the new concept, which based on condition, but it doesn't have anything to do with jump. So let's pause here. We'll talk about the next concept, which is called predicated execution, and talk about how to write a proper assembly code that have if else, can handle loop in the next lecture. If you have any question, give me some time. Don't do in class exercise 7 yet. I'll push the deadline. The next class we'll start doing the in class exercise 7. It has to do with binary arithmetic, but we can do this on Wednesday. That's okay. So I'll be on Discord. I'll switch back to my desktop. Give me a few minutes. Any other question you can put in the chat or ask me now. Let me turn on the volume. Mute myself from my laptop. My bad. Okay. All right. So that's it for this class. If you need to go to the next class, that's fine. You can come back and post the question on Discord. I know that you're not in Discord yet. Can some of you tell what is the channel link? Because I don't have it on hands right now. Or how to join. Can you put that in the chat? If you don't mind, sorry. All right, yeah, so please follow that link to join MUIC Discord. You can ask questions in there. All right, let me stop the recording.